for the anything to superconformal field theory and pattern the systems.
Great. Thanks, Ron. So first of all, I guess I should make some sort of apology. This talk will involve supersymmetry. And geometry, but no supergeometry. On the other hand, it does represent joint work with one of the organizers, Ron Danagi, Ashwin Balasubramanian, and my student Carlos Perez. There's a whole sequence of papers planned, but the one that I will focus on today, the only one that's actually appeared, despite Herculean efforts to the contrary, is that one. And by way of recompense for there being no supergeometry in this lecture, what I propose to do is start out gently by unpacking the following sentence, namely that supersymmetric quantum field theories frequently have moduli spaces of vacua. So that, of course, will lead us into the actual subject of the talk, but I thought it would be nice to at least explain what that sentence means. Otherwise, the rest of the talk is kind of lost. So first of all, we should talk about a generic quantum field theory without supersymmetry. And it will typically have some scalar fields, some operators which transform as scalars under the Lorentz group, which take values in some Riemannian manifold which I'll call m hat. And there's a function called the effective potential, which maps m hat to the positive reals, and the vacua of the theory are the inverse image of 0, which I will eventually call M. Now, without supersymmetry, this is generally rather boring. The zeros of V effective are they're either isolated or sometimes they're related by isometries of m hat. So there's some G which acts on M hat, and the inverse image of 0 is some homogeneous space for G, where H is some proper subgroup of G. This latter case is called spontaneous symmetry breaking by the physicists. And the point is that in this latter case, yeah, you get a whole space of vacua, but they're all related in a sort of stupid way. For every point,
how the first bullet point matches the second one.
sorry?
The zero is isolated or the G-mod H?
Well, you could have isolated zeros, or you could have a whole continuous space of zeros. But without supersymmetry, the latter kind of only happens when there's some symmetry that guarantees it. Okay? And so the G symmetry and the fact that it acts non-trivially is what guarantees that there's this degenerate space of vacua. But then what I'm about to say is that that's still boring for the following reason. So for every choice of point in M, the Hilbert space is recovered by the GNS construction and for the all points in G mod H yield isomorphic Hilbert spaces. So maybe I should say one extra little thing. The vacuum here, which I'll denote by that symbol, is cyclic and separating for the algebra of local observables. And is the unique Poincare invariant vector state in the Hilbert space.
So M is usually homogeneous. M is in the space of the moduli of vacua. It's usually
Well, without supersymmetry, M is either just a collection of points, or it's some homogeneous space. And the homogeneous space case is kind of boring because you pick any point on that space, you get the same physics. Okay, so to get something interesting, this is where supersymmetry comes in. And for the with supersymmetry, we find degenerate different points in the Hilbert space. Well, first of all, we find an M which is not just some homogeneous space, and different points in M yield different Hilbert spaces, yield non-isomorphic. So that's what makes the supersymmetric case interesting. And so M, first of all, is what the physicists call the moduli space of vacua. And that is a little bit of a misnomer. In some cases, M is actually the moduli space for some moduli problem or other. But that's frequently not the case, but the physicists still use the same name, even when it's got nothing to do with any sort of moduli problem. Okay, so that's the first thing. The second thing, is that M has, in general, multiple components. Which the physicists usually call branches. And these meet at some singular locus. And I'll be interested in the particular case where at the most singular stratum of the singular locus, I get a superconformal field theory. Where at this most singular stratum, the Poincare invariance of the theory is enhanced to conformal invariance. And in fact, I'm interested, as I said, in the super case. So that's so the symmetry is some Lie superalgebra. I can't spell today. Algebra, whose odd generators are spinors of SOD, 2. And in general, this algebra contains additional bosonic generators in addition to the conformal generators appearing over here. Those are called the R-symmetry generators. And the algebra, the Lie superalgebra I'll be interested in is the case of 4 dimensions and n, quote unquote, n equals 2, which is the algebra SU2 2/2, whose bosonic generators are SO42, SU2, and U1. And this part here is called the R symmetry. Okay, these are these additional bosonic generators that commute with the conformal transformations. And there are, in the moduli space of vacua, some distinguished branches. The distinguished branches have names, but better than that, I can tell you what distinguishes them. So, So there's the Coulomb branch. On which the SU2 acts trivially. And the U1.
Sorry, I missed why the terminology moduli space de facto is a misnomer?
Well, because this is just some space which is not necessarily the moduli space for any moduli problem. Okay? Sometimes it is, and I think that's where they got the name, but the name stuck even when it's inappropriate. Okay?
Thanks.
Yeah. It's good to be able to talk to each other, so we should establish, common language and whatnot. So this is so U1 acts non-trivially, so it's spontaneously broken. In the language we just described above. And the other interesting branch is called the Higgs branch, where the U1 acts trivially, and the SU2 is spontaneously broken. And now a couple of remarks before I erase the sentence I was trying to explicate. So first of all, on the induced metric, on the Higgs branch, let me call this M sub H and M sub C. So the induced metric on M sub H is hyperkähler. And the induced metric on M sub C is what's called special Kähler. So there's a very beautiful review by Dan Fried on the subject of special Kähler geometry, and I commend that to you. There are various different definitions in the literature. They all turn out to be equivalent, and he explains the equivalence of the various different definitions. And our subject for today is going to be the Coulomb branch. But let me stop and ask if there are any questions before I pass on from the introduction to the actual meat of the matter. All good?
Are there often other branches that you
Sorry? There are other branches which don't have a sort of standard name. They're typically called mixed branches, under which, both SU2 and U1 are spontaneously broken. And there's no sort of uniform zoology of those. But these two distinguished things are kind of distinguished because, there's one or the other of these two subalgebras that I erased is it acts trivially on the corresponding branch. Okay. So in particular, one thing that you learn
Said that this U1 acts non-trivially or trivially. Which U1 is this?
Oh, this was the one in the superconformal algebra that I managed to erase.
So
right?
SU22/4
SU22/2 had SO42 plus SU2 plus U1.
Okay.
And it's that U1 that I'm talking about. Okay? Right. Okay. Very good. So in particular, special Kähler geometry on M is equivalent to an algebraic integrable system which projects to M so X is complex symplectic and the fibers are compact abelian varieties. And they're Lagrangian to this holomorphic symplectic form. So much is completely general. To me, the surprising thing, so this was all worked out in the 90s, a long time ago. But the surprising thing to me was that in examples, ubiquitously one found Hitchin systems, right? That's a class of algebraic integrable systems, but why did that particular class recur with such alarming frequency? It struck me as sort of mysterious, and this was explained in 2009. So Hitchin systems appear ubiquitously in examples, and the answer was provided in 2009 by Gayotto and Gayotto-Murnaitsky, who explained that the many examples come from compactifying the 6D20 theory of type G, some simply laced Lie algebra, on a closed Riemann surface CGN with n marked points. So genus G and n marked points. So the data, of course, is a choice of G, simply laced Lie algebra. And a set of n nilpotent orbits in G, one at each marked point. And with this data, you get some 4D n equals 2 superconformal field theory. And the Coulomb branch geometry is just the Hitchin system, is recovered from the Hitchin system of type G, where on the curve C, where the Higgs field is meromorphic with nilpotent residues at the marked points in the specified nilpotent orbits. Oh, sorry, at the PI, I should be a little bit, in the orbits D of OI, where D, as I will explain in a minute, is the Spaltenstein Barbash Vogin order reversing map from, how did I manage to run out of space? From the set of nilpotent orbits in G to the set of nilpotent orbits in the Langland's dual of G, but of course for simply laced, this is just equal to G. Well, let me tell you a little bit about this. So there's a partial ordering of nilpotent orbits just by orbit closure, and this map reverses that ordering. So that means that the zero orbit gets mapped to the regular orbit. The minimal orbit gets mapped to the subregular orbit, etc. D cubed is equal to D, but D squared is not the identity except outside of type 8. And the image of D are called the special orbits. In G. And I won't give you the general construction, but I'll tell you what it is for type A, where things are simple. For G equals a n minus 1, nilpotent orbits are labeled by partitions of n, or equivalently n box Young diagrams and D takes a partition P to its transpose. So just take the Young diagram and flip it along the 45-degree line, and that gives you what D of that orbit is. And if you apply that operation twice, of course, you get back to what you started with. So D squared is the identity in type A. Okay? Okay, so this immediately poses a very interesting extension of the usual Hitchin story, because these superconformal field theories come in families.
What's nilpotent?
Sorry?
What's nilpotent?
What's nilpotent? I'm looking at, well, okay, let me say it differently. Let's say you knew no representation theory beyond what you learned in elementary quantum mechanics class, okay? So you knew about the representations of SU2, but nothing else. Okay, great. So now someone, some mean person hands you some simple Lie algebra, right, which is not SU2, and says, tell me about its representation theory. Okay, so what would you do? Well, the only thing, the only tool you have is SU2. So you say, well, let me think about all possible ways of embedding SU2 into this Lie algebra. Of course, up to conjugacy, because conjugacy doesn't do anything. And I'll study how stuff behaves under these different SU2 embeddings. Okay? The image of sigma plus is called is a nilpotent element of this Lie algebra, and its orbit under conjugation is called a nilpotent orbit. Okay, and so essentially what I'm telling you is study all possible embeddings of SU2 in the Lie algebra up to conjugacy. Okay. We could spend more time discussing that. I'm happy to do so, but that's what we're doing here. Okay, so the point is the representation theorists actually do what we just said, right? Okay. Right. Okay, so the interesting extension of the usual Hitchin story namely, these SCFTs come in families parametrized by the moduli space of complex structures of the Riemann surface C that we just discussed. And so it's natural to ask, well, how does the Coulomb branch, each one has a Coulomb branch, and how does the Coulomb branch geometry vary as we vary the complex structure of the curve? Right? So that's the obvious question to ask.
So G and N are just two more parameters that you fix to define the theory?
Well, so when I said, I said I start with a curve of genus G with n marked points, right? So G and N are part of the data, right?
But it's not related to the rank of the algebra, for example.
No, that's a separate piece of data. You choose a ADE Lie algebra, you choose a curve of some genus and some number of marked points, and at each marked point, you put a nilpotent orbit, you label that point by a nilpotent orbit in the Lie algebra. This whole collection of data gives you a superconformal field theory, and as you vary the complex structure of the curve C, the superconformal field theories vary in a family. Okay? And now we're going to say, let's look at the Coulomb branch geometry of these guys and ask, how does that vary in this family? So, let me say, I guess I should, first of all, at this point, yeah, so that's interesting, just how do these things vary for smooth curve C, and it's also interesting to try to extend to the boundary of the moduli space, where we include nodal curves. And you might say, gee, that doesn't sound particularly amenable to, the physicist's usual bag of tricks, but in fact, it's the thing that's most amenable to the physicist's bag of tricks, because it's in this nodal limit that we get some weakly coupled gauge theory description, and so that's the one the physicists actually understand. Okay, the interior of the moduli space is hard for us, but the boundaries are easy, so that's actually a good situation to be in, because for the mathematicians, it's the other way around. So,
It's the same process that they do in conformal blocks. In the computer conformal blocks over very reducible curves.
so conformal, the trouble with in 4 dimensions, so there's a whole story associated to decomposing 4-dimensional conformal field, or d-dimensional conformal field theories into conformal blocks. The trouble is, unlike in 2 dimensions, there are an infinite number of conformal blocks, always. And so the people who do this sort of game for a living, there's this whole so-called bootstrap program, people who try to use a unitarity and crossing symmetry in this conformal block decomposition to restrict, but to bound things in conformal field theory in above 2 dimensions. And it's a wonderfully ambitious and surprisingly successful program. You might think you might not get anywhere with such a thing, but they actually do. But that's not going to be my subject here. Let me try to say some things about what the Hitchin system.
Can I ask what the parameter is, like getting small as you go to the boundary?
There's a gauge coupling that becomes small when you go to the boundary, right? And that kind of higher codimension strata of the boundary, where I have multiple simultaneous degenerations, more and more gauge couplings become weak. Right? And so it's a very interesting situation. So anyway, so let me introduce a little bit of notation. So we have our collection of points. We'll let D be the divisor on the curve, which is just the sum of the points. And then, at this point, I'm just going to restrict to type A. So the Hitchin moduli space is the space of Higgs bundles. V and phi, where V is an SLN principal bundle, and phi is an element of H naught of C with values in add V tensor, the canonical bundle. And here I'll make a choice to twist by D. And this is a Poisson manifold. But if we fix the residues of phi at the marked points, to fixed nilpotent conjugacy classes, then we get a symplectic integrable system. And the at this point, I need a better piece of chalk. And the spectral curve in the total space of the canonical bundle twisted by D is some thing that looks like this. Where the AKs live there. And the chi-i's are a bunch of positive integers which are determined by what nilpotent orbits we put at each of the points pi. So the I refers to the ith point, and if we put the residue to be in the regular nilpotent, then chi is 1 for all k. If we put it in the minimal nilpotent orbit, then chi k is k minus 1. And more generally, you write the Young diagram and you fill the first column with 1s and the second column with 2s and so on, and then you skip the first box because that we're in SLN, so everything is traceless, and then you just read off the chi's from just looking at the boxes in the Young diagram. And the Hitchin base, the M that we've been talking about, oh, except here I managed to call it B, weird clash of notation at this point, is just the direct sum k equals 2 on up to n, h naught of c with values in these L sub k's, where the L sub k's are just the things they're where the a's live. K, C, D raised to the kth power, tensor O of minus chi I k pi. And the fibers are just the Jacobian of the spectral curve. And I should say that to get a nice theory, we will impose a condition which we call the OK condition, which is just some condition on the nilpotent orbits, or if you will, on the chi's that follow from the nilpotent orbits, namely that H1 for any smooth curve. Okay, so now finally we're going to take this story, which is fairly standard, and fiber it in families. Right? So this is where we want to go. This is the Coulomb branch, right? I said I would just do the Coulomb branch, right? So what I said is I have this algebraic integrable system. This is equivalent to some special Kähler geometry on the Coulomb branch, right? The equivalence you can read about in Dan Fried's review, right? And so if I tell you this algebraic integrable system, which in this case is a Hitchin system, I've quote unquote told you the Coulomb branch geometry, right? And now again, I'm going to let this algebraic integrable system vary as I vary the complex structure of this base curve C, right? And so the Coulomb branch geometry will vary correspondingly, right? And so I have a family of Coulomb branches with their special Kähler geometry varying as I vary through this family of superconformal field theories. That's the picture. And so let's see, so how can we do that? Mostly it corresponds to replacing Roman letters by calligraphic letters. So what do we do? Well, so we have this universal curve which fibers over MGN, and the LKs to form line bundles curly LK over the universal curve. And all the word, fiber by fiber, everything I've said just carries over. And what we like to do, we like to extend this over the Deligne-Mumford Knudsen compactification of the moduli space, where we allow stable nodal curves. And so, well, I have to then say a little bit more about, how these ingredients are supposed to carry over. So first of all, what's the canonical bundle for a nodal curve? It's the dualizing sheaf whose sections are one forms on the normalization of C with simple poles with opposite residues at the two inverse images of the node. And the naive thing you would write down, now that we've just replaced, Roman letters by curly letters, is to say that I guess I should have written down this formula before. I just take the direct image, so the LKs are now defined. I could just take the direct image of the LKs, and that defines this family of Hitchin bases. But that turns out to not be the answer that we want. And the reason is, so I had this OK condition, which was true for every smooth curve, but it need not continue to hold. With this definition of the LKs, it need not, and in general will not, continue to hold for nodal curves. For nodal curves, the H naught, H1 will be non-zero, and because the index is preserved, the H naught will also jump, right? And so when I take the direct image, I'll get some coherent sheaf rather than a vector bundle, which was kind of what I was hoping for. I should have said I was hoping for a vector bundle, but like something of constant rank, and I don't want the rank to jump when C develops a node and these cohomology groups jump, right? So for a nodal curve, H1 of C and LK is not necessarily equal to 0. So it turns out there's a very cute modification of this story, and the modification goes as follows. Instead of the LKs, we'll replace them with LK primes, which are isomorphic to the L sub k's on the interior, but differ at the boundary. And I'll tell you what they are in a second. In my bundle of Hitchin bases, my bundle of Coulomb branches, is just a direct image of the L prime sub k's. And this is a vector bundle over M bar Gn, where the L prime sub k's, so I think this is a theorem, where the L prime sub k's are L sub k tensored with, sorry, a bunch of things I will have to define, but I promise I will define every symbol there. Let me leave that and erase this. So S is some subset of the collection of points containing at least 2 points. For each such S, there's a component of the boundary where C has 2 components C sub S, which has geometric genus G equals 0, and C prime, which is the rest. And so C sub S contains, I should have said, containing the marked points in S, and C prime contains the rest of the points. Curly C sub S is the Cartier divisor in C bar Gn corresponding to C sub s. And finally, the last symbol there NKS is max of 0 and k minus 1 minus the sum over the points in S of k minus chi I k. So you twist by some components of the universal curve that are supported on this boundary, some multiple of them, and that defines the L primes, and the direct image of that is actually a vector bundle over the moduli space. And this is our bundle of Hitchin bases. And at this point, you may be worried that a lot of symbols, and can one really be concrete here? So for M04 bar, we can compute very explicitly. I should point out this is just the Riemann sphere, so we know all about bundles on the Riemann sphere. That's not too hard. And we can compute very explicitly every bundle on the Riemann sphere, every holomorphic vector bundle on the Riemann sphere splits as a direct sum of line bundles. And so this splitting type characterizes what vector bundle we have, right? So I just had to give you a collection of degrees for the line bundles in question. So let me just, I promise I've now run 5 minutes over, but I promised Ron I would run 5 or 10 minutes over. So let me just give you an example, just to show that we know how to compute stuff. So if I take 4, and now I have to say whether I'm doing nominal, let me say 4, these are the Hitchin pole, the residues of phi are in the regular nilpotent orbit. In, let's say, SL6, just to be to have something non-trivial to write. So the Hitchin base is now, I get a copy of O of 1 from the k equals 2 piece, and then I get 3 copies of O of 1 from k equals 3 plus 4 copies of O of 1 plus O of 2 from k equals 4, and 4 copies of O of 1 plus 3 copies of O of 2 from k equals 5, and then plus, I run out of space as always, 4 copies of O of 1 plus 4 copies of O of 2 plus 1 copy of O of 3 from k equals 6. Right, so it's some fairly large dimensional Hitchin base. I only did this to impress you, with my calculational prowess. But the point is you get very, very explicit bundles over the compactified moduli space that you can compute very precisely. And this is a really interesting and hitherto unknown to me, maybe it was known to others, but hitherto unknown to me, property of this family of superconformal field theories. So this family of superconformal field theories, there's some isolated 4D n equals 2 superconformal field theory called the T6 theory. If you're familiar with Gayotto's paper, it's some theory. So you take 2 copies of the T6 theory and you do an SU6 gauging of some diagonal subgroup of the flavor symmetry, right? And you get this one complex parameter family of SCFTs, which the parameter is the complex gauge coupling of the SU6, the gauge coupling and the theta parameter, okay? And as you vary that gauge coupling, the Coulomb branches fit together to form this vector bundle over M04 bar. Okay, so it's very, very explicit. And there's a very interesting structure to what happens when we hit this boundary that I think for the sake of the audience who's now tired, I will spare you with describing that structure, which I find fascinating, but you maybe too much. But let me just end with like a couple of remarks about where one should go from here. So first of all, as I said, I've just restricted myself in this lecture to type A. Type D and E, there's a similar story, but rather as a bunch of new features, which may make it rather more complicated. Another thing is there a nice definition of the fibers as you go to the boundary of the moduli space? So I've extended the Hitchin base, or the Coulomb branch, to the boundary of the moduli space. Is there some nice definition of the fibers there? And I really think understanding this bundle structure and its generalizations to other moduli spaces beside the 4-punctured sphere is something really interesting that, as I said, I had not appreciated about 4D n equals 2 theories until I got involved in this particular project. So those are a few things to think about for the future, and with that, I thank you for your indulgence, and we can go to lunch soon. Yes?
So, in terms of physics, what does it mean to modify these LK bundles? Because normally they were just traces of multiple powers of the scalar field.
So, there are 2 answers to that. Let me tell the way I came to it. Which has to do with the part of the talk that I left out, which is in this degeneration limit, some gauge coupling goes to 0, and there's sort of some decoupling, right? So there's the theory associated to the left component of the curve and the right component of the curve, and then there's some gauge fields, or the n equals 2 vector multiplets, which are becoming free, right? Okay, so you could ask, what is the theory associated to one of the components, right? It's again a theory of this class S. Class S is the name for this family of theories now, with a choice of nilpotent at the preimage of the node on that side, right? When that nilpotent is not the full puncture, okay, that's precisely when you get this modification. And this modification is precisely the one that changes the orders of the poles to be precisely the one that match some other nilpotent residue rather than the regular nilpotent. Okay? So these ends that appear in this modification are precisely the way you have to change the chi's from being all equal to 1 to being equal to whatever values they're supposed to be for that other nilpotent. So this is the thing that physically, as I said, that you get this kind of factorization of the superconformal field theories or the associated Hitchin systems, and the ends appear in that factorization. Okay? So that's, I think, the best interpretation of it. The way it was used here was just that with this modification, the H1s of the L primes vanish even in the nodal limit. Okay? So that seems like some kind of pointy-headed mathematical thing. I've given a physical interpretation of what that is, right? Namely in terms of this factorization of the superconformal field theories. Okay? But pragmatically, where this was used in this thing was to make the H1s of the L primes vanish even in the nodal limit.
So what's the structure at the boundary that you were sparing us?
Well, so as I said, what happens is some gauge coupling goes to 0, right? And so if this is a separating node where the curve separates into two pieces, right? Then there's some superconformal field theory associated to the piece on the left, and a now I've got this backwards. This is your right and my left. Okay, right. Super theory on the left, theory on the right, and the Hitchin integrable system, or at least the base of the Hitchin integrable system, because I haven't really told you what I'm supposed to do with the fibers. But the base also has this factorization, where I have some base parameters associated to the superconformal field theory on the left, some base parameters associated to the superconformal field theory on the right, and some base parameters which are associated to the gauge multiplets in between. Okay? And they are precisely in correspondence with the Casimirs of the gauge group in question, right? So we said SL6 was our example, right? So we'd have Casimirs of degrees 2 through 6, right? Because it's rank 5, right? And so we'll have, in that case, 5 base parameters that are kind of common to the two sides, and we'll have the guys which are associated to the T6 theory on the left and the T6 theory on the right.
So I have a question. So since this theory model is based on SU2/2, meaning the superconformal.
Right,
Can you view also this construction from the CCFT point of view?
From the what?
The CCFT point of view, from the correspondence. From the dual theory. Can you see this structure of the model space?
Well, I mean, so the superconformal algebra is just whatever it is, SU2, 2/2, that's the n equals 2 superconformal algebra. What I've been talking about is a class of theories which have that as their symmetry algebra, which happen to come from this fancy construction involving 6 dimensions and blah, 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 right? Due to Gaiotto and company. But of course, the data, so there's this huge rich class of theories where you pick a genus, or you pick simply laced Lie algebra, you pick a genus, you pick a number of punctures, and you pick a collection of nilpotent orbits in that Lie algebra, and that gives you a family of theories, all of which have SU2, 2/2 as their superconformal algebra, right? So as the superconformal algebra is common to everything in this class. Is that?
No, I mean, can you understand from the ADS point of view, I mean, for the dual theory?
Oh, ADS. So, okay, brilliant. So let me give you the simplest example of this. So let's take genus G with no punctures. Okay, genus G greater than or equal to 2. The resulting SCFT is something whose large N limit was discovered by Maldacena and Nunez. Okay, so, but of course you could do it for, not just for SUN, for N large, but for any N. That family of theories, as I said, in the large N limit, has this ADS dual that Maldacena and Nunez wrote. And so this is the N equals 2 supersymmetric Maldacena and Nunez. They discussed both N equals 1 and N equals 2 supersymmetric solutions. The N equals 2 supersymmetric one is just the theory I've been describing with no punctures. Okay? The only wrinkle is that you can not just do it for type A, which is what they did, but for types D and E as well. And you can do it for finite N, not just for infinite N. Okay? So so that special case of this construction has a beautiful ADS dual discovered way back when, right? And I think that's actually the pattern. So in fact, what that is in terms of the language I just used to describe this thing, right? There's this thing called the Tn theory, okay? And so if you take 2G minus 2 copies of the Tn theory, and gauge 3G minus 3 copies of SUN, okay, you get the Maldacena-Nunez theory. You look puzzled.
I was just wondering where those numbers came from.
Well, consider taking a genus G surface with no, closed Riemann surface with no punctures, and degenerating it, right? So the complete degeneration limit you can think of as a bunch of 3 punctured spheres, glued together at the nodes, or just trivalent graphs. Okay, so look at a trivalent graph of genus G, right? And count the number of edges and the number of nodes. Okay, the number of edges is 3G minus 3, and the number of nodes is 2G minus 2. Each node is one of these Tn theories. Each edge is an SUN. Okay, and the different ways of drawing such graphs, because there's more than one if G and N are big enough, correspond to S-dual degeneration limits of this family of SCFTs.
So they're all related.
They're all related. They all fit inside this big MG0, family of theories, right? But at various multiple intersections of the boundary, we get these different descriptions in terms of the Tn theory and SUN, bunch of SUN gauge groups.
Okay, then let's Jacques again.
Thanks.
Can I ask one more question? I didn't want to ask because it's more technical. So again, physically, if one of the LKs develop H1,
Right.
which is what we don't
Yeah.
want, again, what does it mean physically? What went wrong? Suppose I was trying to describe So all of these sections, the H0s, they form a commuting set of Hamiltonians,
Right.
regardless of H1.
Right.
So what
So, yeah, so that's a super interesting question. There are various notions of bad theories. Which, well, I'll tell you an experimental fact for which I don't have a proof. The experimental fact is that whenever I have a theory where the H1s are non-zero, so I could have had a non-zero H1 on a smooth curve,
Yeah.
right?
Yeah,
Okay,
yeah, sure.
right? If H1 is non-zero, then the superconformal index, so there's a formula for the superconformal index in class S,
Right.
that formula diverges.
Okay, yeah, yeah.
Okay? And these are not obviously related statements because the superconformal index has to do with the Higgs branch and you know, Schur operators, operators in various short multiplets, right? And this thing has to do with the Coulomb branch, right? And so there's no obvious reason why these two statements are related, but they are experimentally at least, precisely equivalent, right? So H1 non-zero if and only if the superconformal index diverges. I don't, like I said, I don't have a proof of that, but I swear it's true.
Yeah, because it feels like there's some kind of, you see this problem comes back, I mean, even yesterday, whenever this higher cohomology,
Right.
sometimes some certain cohomology non-vanishing, that means certain maps cannot be defined, either not surjective, not injective, or
Right.
being obstructed. Yeah, it seems to me that there's just a big, I don't
Well,
know.
yeah, so I don't, I mean, there are various pieces of the construction which are much nicer, you know, which you could in principle contemplate doing even when H1 was non-zero, but which are much nicer when it's zero. Okay, so that's certainly true. But, you know, that's some mathematical nicety. It's not obvious like why that's a requirement. And the one thing I can say is that the superconformal theories have this property that the superconformal index converges if and only if H1 vanishes.
Okay. Yeah, okay.
Okay.
Yeah, okay,
Okay.
thanks. Well, I think you should take on the.
Oh, yeah, probably. The guy never reappeared. Let's see. Switch it off. Do you know where the switch is?
I think it's here.
Is that it?